Hello, welcome back to Sleep Science. Wherever you are right now, this is a good place to be. Tonight, 100 facts about the deep ocean. Each one true, each one quiet, each one worth sitting with for a moment. Settle in. The ocean floor is the largest ecosystem on Earth, and we have explored less of it than the surface of the moon. Less. The moon, which is 384,000 kilometers away, we know better than the bottom of our own ocean. What we do know, though, is extraordinary, and that is where tonight begins. Start here, with something simple, something almost too large to hold in the mind all at once. So let it come slowly. More than half of everything you can see, if you could see the whole Earth from far enough away, is ocean. Not just ocean at the edges, decorating the land like a border. Ocean as the main event, land as the afterthought. Somewhere over 70% of this planet's surface is water, and most of that water is deep. Deep enough that light doesn't reach it. Deep enough that pressure would fold a human body the way you might fold a piece of paper, without effort, without struggle, just quietly. Physics doing what physics does. You're lying somewhere warm right now. Maybe there's a blanket around you. Maybe a small light somewhere in the room. Or maybe none at all. Just the blue glow of a screen fading as your eyes get heavy. Notice that. Notice the air on your skin, the specific temperature of this exact moment. Because in a few minutes we're going to leave it, in our minds, and go somewhere very different. And it helps to remember, every so often, that you can always come back. So, the ocean. We've mapped less than 25% of its floor in real detail. Actual detail. The kind where you could look at a stretch of seafloor and say, yes, that is a ridge, that is a canyon, that is flat sediment plain, stretching for kilometers. Most of the rest is guessed at. Inferred from satellite gravity measurements, from sonar pings bounced off in wide, imprecise sweeps, which means, somewhere down there right now, there are mountains nobody has ever seen, valleys with no name, whole geological features larger than countries, sitting in total darkness, unmapped, unknown, and yet entirely real. Waiting isn't the right word, because waiting implies awareness, and the ocean floor has none, but it's there. Patient in the way only something without impatience can be. Let's go to the floor itself for a moment, because there's something almost funny about it, in a quiet way. If you took every mountain range on land, the Andes, the Rockies, the Himalayas, and you compared them to what's hidden under the ocean would win without much contest. There's a mountain range down there so long it wraps most of the way around the planet. The mid-ocean ridge, over 65,000 kilometers of continuous mountain chain, snaking through the Atlantic, down through the Indian Ocean, curling into the Pacific. It is the longest mountain range on Earth, and almost nobody has ever seen it. Not with their own eyes, not directly. It exists the way a rumor exists, constantly, but just out of reach. Picture it for a second, not as a diagram, not as a line on a map. Picture actual rock, actual stone ridges rising kilometers above the surrounding seafloor, cliffs and valleys and slopes, all of it submerged under water, so deep that no sunlight has ever touched it. Mountains that have never been rained on, never had wind, never had anything walk across them. Just water and pressure and time. And that connects to something else. Something that always surprises people the first time they hear it clearly stated. We know the surface of the moon better than we know the bottom of our own ocean. We have high-resolution maps of nearly the entire lunar surface. Every crater, every ridge. We can plan a landing site on the moon with more confidence than we can describe what's sitting at the bottom of most of the Pacific. Which is strange, if you stop and actually feel it, rather than just hear it as a fact. The moon is 250,000 miles away. The ocean floor is beneath ships that cross it every day. And yet one is more familiar to us than the other. It isn't that the ocean is farther, it's that it's harder. Pressure, darkness, cold, the simple physical difficulty of being there at all, these things have kept large portions of our own planet stranger to us than another world entirely. Let's sit with this for a moment before we move. There is a place on this planet, right now, tonight, while you are lying there with your blanket and your soft light, that no human eye has ever seen directly, not once, ever, in the entire history of our species. And it isn't far away, in the way distant galaxies are far away. It's a few kilometers straight down, in water that has always been here, connected to the same ocean whose edge you might have stood on as a child. That's not meant to unsettle you. It's meant to feel like a kind of gift, actually. A reminder that the world still has rooms nobody has opened, that mystery hasn't run out, that there is still a last frontier, and it is not somewhere distant and cold and empty. It is right here, close, and full of life. Because here's the part that changes everything, the part we're going to keep circling back to tonight in different ways. That darkness isn't empty. That's the surprise underneath all of this. You'd think that a place with no light, crushing pressure, near freezing temperatures, would be closer to a vacuum than a home, and instead it turns out to be one of the richest, strangest, most quietly alive places we've ever found. Let's go there slowly, layer by layer. The way light actually fades as you descend, because that's the true order of things, and there's something comforting about following the real shape of the world rather than jumping straight to the extremes. Right at the surface, where you've probably swum before, where sunlight turns the water gold and green, that's called the sunlight zone. It only goes down to about 200 meters, which sounds like a lot, until you remember the ocean averages nearly 4 kilometers deep. Almost all of the color, almost all of the plant life, almost everything we picture when we picture the ocean happens in that first thin skin. Below 200 meters, something changes. Not suddenly, gradually, the way a room dims as the sun sets outside, so slowly you almost don't notice until you look up and realize it's nearly dark. This is the twilight zone. It runs from 200 meters down to about 1,000, and down here, light still exists, technically, but it's faint. Blue, mostly, because blue light survives longer in water than any other color. Reds and yellows get absorbed almost immediately, swallowed by the first few meters. Blue keeps going, which is why, if you've ever seen photographs from underwater at depth, everything looks bathed in that same cool, deep blue, even without any artificial light at all. By the time you reach 1,000 meters, though, blue runs out too. This is where the sunlight zone gives way completely to true darkness, and we cross into what's called the midnight zone. From 1,000 meters down to about 4,000, no sunlight penetrates this deep, not a trace. Any light down here comes from the creatures themselves, which we're going to spend real time with tonight, because it's one of the strangest, most beautiful things this planet does. Temperature in the midnight zone hovers somewhere close to 4 degrees Celsius. Cold, but not the coldest it gets. Steady, unchanging. It doesn't get colder in winter or warmer in summer, because none of that reaches this deep. The seasons that shape your entire life up here mean nothing at 4,000 meters down. There's just the same temperature, the same darkness, the same pressure, forever, or close enough to forever that it might as well be. Beyond 4,000 meters, we reach the abyssal zone, which runs to about 6,000. This is where things get genuinely strange, where pressure becomes almost unimaginable, and life becomes almost unimaginably patient. And past 6,000 meters, only in the deep trenches that cut into the ocean floor like scars, we reach the hadal zone, named after Hades, the underworld, which feels almost too on the nose until you actually learn what's down there and realize the name might be more honest than poetic. Notice your breathing for a second, in and out. Notice that you can, that's not nothing. Down at those depths, breathing the way you're breathing right now would be instantly, catastrophically impossible. Not because there's no air, because the pressure would collapse a human chest before a single breath could finish. It's strange to think about breathing as a privilege, but maybe it is one, quietly, all the time, and we just don't usually notice. So let's talk about pressure properly, because it's going to come up again and again tonight, and it deserves to be understood, not just mentioned. At sea level, right now, wherever you're lying, the air above you is pressing down with a certain weight. You don't feel it, because your whole life has been lived inside it. It's the baseline, it's normal. But that pressure is still there, still real, about 1 atmosphere's worth of force pressing on every surface of your body, all the time, from every direction, and your body pushes back with equal force, so it all balances out into something you never think about. Now go underwater. Every 10 meters you descend, you add roughly another atmosphere of pressure. 10 meters, 2 atmospheres, 20 meters, 3. It adds up fast, and it adds up mercilessly. By the time you reach the deepest point in the entire ocean, a place called Challenger Deep, at the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure is over 1,000 atmospheres. 1,000 times the pressure sitting on you right now, all at once, from every direction, forever. It's hard to make that number mean anything just by hearing it, so try this instead. Imagine balancing the weight of about 50 jumbo jets on a single point the size of your body, not far above you, directly on you. That's the kind of force we're talking about. And yet, down there, in that unimaginable crushing dark, there is still life, not thriving in the way a coral reef thrives, not colorful, not loud, but alive. Quietly, stubbornly alive, in conditions that would seem, on paper, completely hostile to the very idea of life existing at all. Which brings us, gently, to Challenger Deep itself. It's the deepest known point in all of Earth's oceans, part of the Mariana Trench, out in the western Pacific, almost 11,034 meters at its deepest measured point, though the exact number shifts slightly depending on the survey, because measuring something that far down, through that much water, is its own kind of miracle of engineering. If you took Mount Everest, the tallest mountain on land, and dropped it into that trench, its peak would still be over 2 kilometers underwater. The tallest point on Earth would vanish, swallowed whole, with room to spare. For most of human history, that place was simply unreachable. Not unreachable like difficult. Unreachable like the idea hadn't fully formed yet, because the technology to survive down there didn't exist. And then, in 1960, 2 men changed that. Jacques Piccard and Don Walsh climbed into a vessel called the Trieste, a bathyscaphe, which is a strange word for a strange kind of machine, essentially a steel sphere hung beneath a massive float, and they went down through the sunlight zone, down through the twilight zone, down into the endless midnight zone, and kept going, past where anyone before them had ever gone, down into a darkness with names attached to nothing, into pressure that had never before been tested against a human being at that specific depth. It took nearly 5 hours to descend. 5 hours of sinking slowly through increasing dark, the little sphere creaking under stresses that would have been fatal to almost any other structure built by human hands at that time. And when they reached the bottom, they didn't find nothing. They found, of all things, a flatfish, some kind of sole or flounder, resting on the sediment, watching them, or seeming to, before swimming calmly away. Whether that particular sighting was later disputed by other scientists or not, and it has been, gently, over the decades, the moment itself stands. Two men in a steel ball at the very bottom of the world, looking out a tiny viewport into absolute blackness, finding that even there, life had already arrived first. They stayed only about 20 minutes before beginning the long ascent back. 20 minutes after years of preparation and hours of descent at the deepest place on Earth. It's strange how brief the actual moment of arrival often is, compared to everything it took to get there. Maybe that's true of a lot of things in life too. And then, for decades after that, almost no one went back. Challenger Deep became this strange, almost mythic place, visited once, then left alone, too difficult, too expensive, too dangerous to return to casually. 52 years passed before another crude dive was made to that same trench, and this time it was made alone. James Cameron, yes, the filmmaker, though by that point also a serious deep-sea engineer in his own right, descended solo in 2012 in a custom-built vertical torpedo-shaped submersible called the Deep Sea Challenger. Alone, for a solo dive that took roughly 2.5 hours to descend, spending several hours at the bottom conducting research, collecting samples, filming footage of a place almost nobody had ever documented directly, before ascending again. There's something worth sitting with in that image. A single person, alone, in a tiny vessel, at the very bottom of the ocean, farther from any other human being than almost anyone in history has ever been, and yet closer, in another sense, to the true unexplored heart of this planet than anyone alive, not in space, not on some other world, here, on Earth. In our own backyard, in the truest sense, if your backyard happened to be 70% of the entire surface of your home, let your body settle back into the room for a second. Feel the actual, present weight of the blanket if you have one, the actual air temperature around you, ordinary and warm and safe, one atmosphere, unchanging, undramatic. That contrast is going to keep showing up tonight, over and over, gently, not to frighten you, to make the safety of exactly where you are feel more clearly, more gratefully, real. Because here's a thought worth carrying forward as we keep descending together tonight. Nearly the entire habitable volume of this planet isn't on land, and isn't even in the shallow parts of the ocean most of us picture when we hear the word ocean. It's down there, in that vast, dark, cold volume of water that makes up most of what our world actually is, by sheer physical space. We live our whole lives on a thin sliver of surface, sunlit and comfortable, while the actual largest habitat on Earth stretches on beneath us, patient, mostly unseen, mostly unknown, and absolutely, undeniably alive. And that's where we're headed next, down into that twilight, where the color blue becomes the last color left, and where something strange and beautiful begins to happen to the animals that live there. Down there, in that blue and fading light, something like 76% of all deep-sea animals make their own light. Not borrowed light, not reflected light, their own. Say that again slowly, because it deserves to be said slowly. 3 out of every 4 creatures living in that twilight, in that midnight, in that abyss, produce light from inside their own bodies. That it isn't rare down there. It isn't a curiosity. It's closer to the rule than the exception, which means if you could somehow float quietly through the dark at 1,000 meters, most of what surrounded you would eventually, faintly, begin to glow. It comes from chemistry, not magic, though the line between the two can blur a little when you actually understand it. Two molecules, mostly, one called luciferin, one called luciferase. The luciferin reacts with oxygen, and the luciferase acts almost like a hand cupped around a small flame, guiding the reaction, shaping it, controlling exactly when and how the light appears. Different creatures use slightly different versions of this same basic idea, evolved separately, over and over, in different branches of the tree of life, all arriving independently at roughly the same solution, which is its own kind of quiet wonder. Nature finding the same answer again and again, without anyone telling it to. And almost all of it is blue. That's not an accident either. Remember the light fading as we descended, red disappearing first, then orange, then yellow, until only blue was left before the darkness swallowed everything. Blue survives longest in water. It travels farthest. So evolution, patient and unthinking and endlessly practical, tuned nearly every bioluminescent creature down there to produce that exact wavelength, because that's the wavelength that actually gets seen. A red light down there would be almost pointless, absorbed within meters. Blue carries, blue matters. So blue is what nearly everything makes. Feel the room around you again for just a second. Notice any light nearby, however small. A charging cable's glow, a sliver of light under a door. Up here, light is so abundant we barely register it as a thing at all. We just live inside it. The way fish up in the sunlit shallows live inside warmth and color, without a second thought. Down at 1,000 meters, light is the rarest, most precious currency there is. And so almost everything down there has learned to make its own. Let's meet some of them properly, not as facts to check off, as things to actually picture, slowly, the way you'd picture an old photograph someone described to you in detail. Start with the giant squid, because it's the one that haunted human imagination the longest before we ever truly saw it. For centuries, sailors told stories, enormous arms rising from the water, wrapping around ships, dragging things down into the dark, sea monsters, krakens, myths passed from voice to voice until nobody quite knew where the myth ended and something real might have begun. And there was something real underneath it, as there so often is with the old stories. The giant squid is real. It can grow to around 13 meters in length, tip of the mantle to the end of its two long feeding tentacles. 13 meters. Longer than a city bus, living in near total darkness, in the deep twilight and midnight zones, rarely if ever coming close enough to the surface to be seen by human eyes under normal circumstances. For most of history, we only knew it from what washed ashore. Dead specimens, damaged, decomposing, found on beaches or tangled in fishing nets, offering only fragments of the truth. Beak, tentacle, a great, strange eye, sometimes as wide as a dinner plate, staring up from the sand at people who had no idea, really, what kind of animal it had belonged to. It wasn't until 2004 that anyone managed to photograph a live giant squid in its own environment. Japanese researchers, after years of patient effort, finally captured images of one in the wild, alive, moving through the dark exactly where it belonged. Video footage of a live one came a few years after that. Which means, and this is worth sitting with, that for the vast majority of human history, this animal existed only as legend or as corpse. We are among the very first generations of humans ever to see what it actually looks like alive, which is a strange kind of privilege when you think about it. Something people wondered about, feared, wrote stories about for thousands of years, finally, quietly, confirmed real within living memory. Your grandparents might have grown up in a world where the giant squid was still, officially, mostly myth. And it isn't even the largest squid down there. The colossal squid, a slightly different animal living deep in the cold waters around Antarctica, is shorter overall, but heavier, bulkier, and carries something extraordinary. The largest eyes of any known animal on Earth. Eyes that can grow to nearly the size of a basketball. Enormous, dark, built for a single purpose. Gathering every last photon of the faint blue bioluminescent light drifting through that endless midnight, searching, perhaps, for the shape of a predator, or the shape of prey, or simply the shape of anything at all, in a world built almost entirely from the absence of shape. Imagine having eyes built for a world with almost nothing to see, and still needing them larger than any other creatures, precisely because of how little light remains to catch. Let's step back into the room again for a breath. You have eyes built for sunlight, for color, for a world drenched in visible detail every single day of your life. It's such a basic thing, so constant, that it stops feeling like a gift at all. It just feels like default. And somewhere in the cold, dark south, there's an animal whose eyes are built the opposite way, for scarcity instead of abundance, and they had to grow enormous just to make scarcity survivable. There's something almost tender in that, if you let yourself feel it that way instead of just filing it away as biology. And speaking of things built specifically for the dark, we should talk about the anglerfish, because it might be the single most recognizable resident of this whole strange world, even if most people only know its silhouette. That small glowing lure dangling in front of a mouth full of needle teeth. The light itself isn't the fish's own tissue glowing. It comes from bacteria, living symbiotically inside a special organ called the esker, right at the tip of a thin spine that extends forward from the fish's head, like a fishing rod cast out in front of its own mouth. The bacteria glow, steadily or in pulses depending on species, and smaller creatures, drawn the way anything in darkness is drawn toward the only light available, drift closer, curious, until they're close enough for the anglerfish to strike. It's a small, quiet trap, built from cooperation between two very different forms of life, fish and bacteria, working together in the dark for the exact same goal: survival, shared. But the truly strange part of the anglerfish's story isn't the lure at all. It's what happens between males and females. In most anglerfish species, the females are the ones we picture: round, ominous, several centimeters to sometimes far larger, carrying that glowing lure. The males, by contrast, are tiny, a fraction of the female's size. Barely more than a set of eyes, a nose built for scent, and a driving need to find a mate in a world so dark and so empty that the odds of finding another anglerfish at all, let alone one of the opposite sex, are almost unthinkably small. So in some species, when a male finally does find a female, he bites down and never lets go. Over time, his body begins to fuse with hers, skin merging with skin, blood vessels connecting, so that eventually his own circulatory system links directly into hers. His eyes atrophy, his fins atrophy. Most of his internal organs, the ones he no longer needs, slowly disappear until what remains is barely recognizable as a separate creature at all. Just a small, permanent attachment riding along on the female's body for the rest of her life, providing nothing but a steady, on-demand supply of sperm whenever she's ready to spawn. It sounds almost unbearably strange when you first hear it, almost grim, but it's worth sitting with a little longer than that first reaction, because underneath the strangeness is something closer to a solution than a horror. In a world this vast, this dark, this empty of other members of your own species, finding a mate, even once, might be the rarest event of an entire lifetime. And so evolution, endlessly practical, found a way to make sure that once found, that connection would never have to be found again. Let's come back to the room now, gently, because that was a heavy little corner of the ocean to sit in. Feel your own breathing again. Notice that you are, right now, a single complete organism, separate, whole, unconnected to anyone else's body, free to move through your life on your own terms. That's not something anglerfish get to take for granted, but you do, and it might be worth simply noticing that, the way you'd notice warmth after being told a story about cold. There's another animal down there, close in spirit to the anglerfish but stranger still in its own quiet way, called the vampire squid. And here's the first small twist. It is not, technically, a true squid. It is not, technically, a true octopus either. It belongs to its own separate order entirely, an ancient lineage that split off from other cephalopods so long ago that it's often described as a kind of living fossil, a creature that's remained largely unchanged since long before most of what we'd recognize as the modern ocean existed. Its name suggests menace, dark red skin, webbing between its arms lined with spines, an appearance somewhere between squid and umbrella and shadow. But the reality is almost gentle by comparison. The vampire squid doesn't hunt in any aggressive sense. It drifts, mostly, through the oxygen minimum zone, that band of water between 200 and 1,000 meters, where oxygen levels drop so low that most other predators simply cannot survive there long enough to bother it. It feeds not by chasing prey, but by collecting marine detritus drifting down from above, the same slow, endless snowfall of organic material we'll come back to properly a little later tonight. When it feels threatened, it doesn't fight, and it doesn't flee in any dramatic sense either. It turns itself inside out, pulling its webbed arms up and over its own body like a dark umbrella, closing the wrong way round, exposing the spines along the underside of its arms, appearing suddenly larger, spikier, stranger than before. And if that display doesn't work, it releases not ink, because ink is nearly useless in total darkness, but a cloud of glowing bioluminescent mucus instead, confusing whatever was hunting it, buying just enough time to drift quietly away into the dark it came from. There's something in that which feels almost peaceful compared to everything else down here. A creature that survives not through violence, but through stillness, through low oxygen tolerance, through a strange defensive light show instead of teeth. Even in a world this harsh, not everything survives by being fierce. Some things survive simply by being quiet and patient and difficult to catch. And that idea, patience as a survival strategy, is going to come back again and again tonight, in stranger and stranger forms. Let's talk about teeth for a moment now, because down here they take on shapes that would look almost impossible anywhere else. The fangtooth fish is small, genuinely small, rarely longer than about 16 centimeters, small enough to fit easily in the palm of your hand, and yet it carries teeth so disproportionately large that it cannot fully close its mouth. Its lower fangs are so long that special sockets have evolved on either side of its brain, just to give those teeth somewhere to slide into when the jaw closes. Without those sockets, the fangtooth would, quite literally, stab itself in the brain every time it closed its own mouth. Proportionally, it has the largest teeth of any fish in the ocean. And it needs them, because down at those depths, in that oxygen minimum zone stretching out into the deep midnight beyond, meals are rare, calories are precious, and when something finally does drift close enough to catch, there's no room for a miss. A creature that might only encounter food once every few days, or longer, cannot afford a gentle bite. It needs a hold that does not fail. Picture something the size of your palm, dark, ancient-looking, drifting nearly motionless in absolute blackness, patient in a way almost nothing on the surface world ever has to be, waiting, sometimes for what would feel to us like an unbearable length of time, for a single small shape to drift within striking range. And when it finally does, there is no hesitation left in that bite at all. Let's soften for a moment, though, and meet something stranger but gentler. The barrel-eye fish, sometimes called the spookfish, which carries one of the strangest heads of any animal on this planet, on land or in water. Its head is transparent, not just its eyes. Its entire skull, dome-shaped and clear like a piece of glass, allowing you to look directly into its head and see its two barrel-shaped, tubular eyes sitting inside, glowing faintly green in most specimens, oriented not forward, the way eyes usually are, but upward, toward the surface far above, scanning constantly for the faint silhouettes of prey passing overhead, backlit against whatever last trace of light manages to filter down that far. For a long time, scientists actually believed the barrel-eye's eyes were fixed permanently in that upward position, forever staring toward a surface it would never reach. It wasn't until researchers managed to observe a living specimen, kept successfully in a laboratory setting, rather than pulled apart from a damaged trawl-caught corpse, that the truth became clear. Those tubular eyes can actually rotate, forward and upward, swiveling inside that transparent dome of a skull, allowing the fish to look up while searching for shapes above, and then look forward when it's actually time to approach and feed. Imagine having a window built directly into your own skull. Imagine being able to look, quite literally, straight through your own head. It sounds almost like something from a strange dream, and yet it exists, right now, drifting quietly through the twilight zone, solving a problem, how to see clearly in near darkness, while still protecting delicate eyes from the drifting bodies of siphonophores and other stinging creatures nearby, in a way evolution alone could have produced, patiently, over unthinkable stretches of time. Let's return to the room again, gently, because we've been moving through some strange corners of the dark. Notice for a moment your own eyelids, how simple they are, how completely you take for granted the fact that when you want to close your eyes, you simply do, and the world goes dark on your terms, not the ocean's. There's a small, quiet comfort in that, a softness available to you right now that took the barrel eye an entire transparent skull to approximate in its own strange, patient way. One more mouth to meet before we drift onward, and it might be the strangest of the strange. The gulper eel, sometimes called the pelican eel, for a very good reason once you see it. Its most defining feature is a mouth so enormous, so loosely hinged, so wildly out of proportion to the rest of its long, thin, almost ribbon-like body, that it can unhinge and expand to swallow prey significantly larger than the eel itself. Think about that for a second, slowly. Not prey the same size as itself, prey larger. An animal built almost entirely around the idea that food is so rare down here, so unpredictable, so few and far between, that when an opportunity does arrive, size should never be the limiting factor. Better to have a mouth so absurdly expandable that nothing edible ever has to be passed up, simply because it seemed too big to fit. Its stomach, too, can stretch remarkably, accommodating meals that seem almost cartoonishly oversized compared to the eel's own slender frame. And much like the anglerfish, it carries a small bioluminescent light at the very tip of its long, whip-like tail, likely used to lure prey close, or perhaps to attract other gulper eels, in a world where finding another one of your own kind is rare enough to matter. There's a pattern quietly forming here, if you've been following along. Rarity, scarcity, patience. Nearly every strange adaptation we've met so far, the enormous eyes, the impossible teeth, the expandable mouths, the single use of light in total dark, all of it circles back to the same underlying truth about this part of the world. Down here, resources are so scarce, encounters are so rare, that evolution has had to solve the same basic problem again and again, in wildly different ways, across wildly different creatures. How do you survive in a world where almost nothing happens? Almost all of the time. And one answer, it turns out, is simply this: slow down. Deep-sea fish very often have extraordinarily slow metabolisms compared to their shallow water cousins. Everything about them runs at a gentler pace. Heart rate, growth, movement itself, often reduced to slow, minimal drifting rather than active, energy-hungry swimming. It's a direct response to how little food actually reaches them. If meals are rare, then burning energy quickly is a death sentence. So many deep-sea creatures have simply, patiently, evolved to need less, to want less, to live slower lives, stretched out over far longer spans of time than we'd expect from looking at their size alone. Some deep-sea fish, small, unremarkable-looking creatures that would seem to belong to short-lived species if you judged only by size, actually live for over a century, quietly, slowly, drifting through decade after decade of that same unchanging cold and dark, while entire human generations rise and pass above them, utterly unaware. And then there's the Greenland shark, which takes this idea of slowness to a scale that's genuinely difficult to hold in your mind without pausing. The Greenland shark lives in the cold, deep waters of the North Atlantic and Arctic, growing slowly, moving slowly, reproducing slowly, existing, in every measurable way, at a pace utterly unlike almost anything else we recognize as alive. It can live for over 400 years. Let that settle for just a moment before moving forward, because it deserves a moment of stillness rather than being rushed past like just another number in a long list. 400 years. Scientists used a technique involving the lens of the shark's eye, layers accumulated slowly over its lifetime, much like rings in a tree, combined with radiocarbon dating, to estimate the ages of several Greenland sharks caught incidentally during other research. One individual, the oldest ever estimated this way, came back with an age of roughly 512 years. 512 years old. That shark, if the estimate holds, was already alive before many of the events we consider ancient history in a Western timeline. Alive before certain famous ships ever set sail. Alive through entire centuries of human wars, inventions, empires rising and falling on the surface far above it, while it continued, slowly, patiently, entirely unaware and unaffected, growing perhaps a single centimeter every year, drifting through cold, dark water, in a life so long it becomes difficult to even compare to anything we experience personally. Feel your own hands for a second. However old you are right now, however many years you've lived, however long or short that feels some nights, there is a creature alive today, right now, this very evening, somewhere in the cold, dark Atlantic, that was already old when your great-great-great-grandparents were being born. Older still than that, likely, depending on which estimate proves most accurate over time. It doesn't make your life smaller to know that. If anything, it might make this exact moment, this blanket, this room, this particular quiet evening you're spending right now, feel a little more precious, because, unlike the Greenland shark, you don't have 500 years to spend carelessly. You have this one, ordinary, quiet night. And that's not a small thing, that's the whole thing, and that slowness, that patience, that willingness to let time stretch out far longer than seems reasonable, is going to come up again, differently, when we reach the very bottom of the trenches later tonight. But before we go any deeper, there's a much simpler story waiting for us, still up here in this same drifting twilight, about where all this life is actually getting its food from in the first place. Because nothing down here is growing plants of its own. Nothing down here has sunlight to farm, and yet somehow none of it starves entirely. Somehow none of it starves entirely, and the answer, it turns out, is falling from above, constantly, silently, the way dust settles in an empty room, except this dust never stops falling, and this room is the entire ocean. It's called marine snow, and the name is almost too gentle for what it actually is, though maybe that gentleness is exactly right, because there's nothing violent about it. Marine snow is the slow, endless drift of organic material sinking down from the sunlit surface far above. Bits of dead plankton, fragments of waste, tiny flakes of decaying tissue, mucus, shed skin cells, the accumulated debris of an entire living ocean above, falling, always falling, in a snowfall that has never once stopped since long before there were humans to notice it. It can take weeks for a single flake to drift from the surface down to the deep sea floor. Weeks for something the size of a grain of dust, sinking slowly through kilometers of increasingly cold, increasingly dark, increasingly pressurized water, drifting sideways with currents, spinning, breaking apart, being eaten and partially digested and released again by smaller creatures along the way, until whatever remains finally settles onto the sediment far below. And that slow, endless snowfall is, for most of the deep sea, the only food there is. Think about that for a second, slowly, the way we've been trying to think about most of this tonight. Nearly every ecosystem you've ever pictured, forests, grasslands, coral reefs, gets its energy directly or indirectly from sunlight, from plants growing right there, converting light into food in real time. The deep ocean doesn't get that option. There is no sunlight down there to grow anything at all. So instead, it depends entirely on scraps, on leftovers, on whatever manages to fall, slowly, patiently, from a world it will never see, drifting down like a gift from somewhere its inhabitants can only imagine. Feel that for a moment as something almost tender, an entire ecosystem, vast beyond imagining, kept alive not by anything happening within it, but by the quiet, constant generosity of a world above it, letting go of what it no longer needs. But marine snow isn't the whole story, because in certain places on the ocean floor, life found another way entirely, a way that owes nothing to the sun at all. In 1977, scientists exploring the Galapagos Rift aboard a submersible called Alvin made a discovery that genuinely reshaped how we understand life on this planet. They found hydrothermal vents, cracks in the ocean floor along the spreading edges of tectonic plates, where seawater seeps down into the crust, gets superheated by magma far below, and rushes back up again, carrying with it a rich, mineral-heavy chemical soup, hydrogen sulfide chief among them, in plumes that can look, from a distance, almost like black smoke pouring from chimneys built of stone. And clustered around those vents, the scientists found something that shouldn't have been possible by the assumptions of the time. Life. Dense, thriving, abundant life. In a place with no sunlight whatsoever, no marine snow reaching down in any meaningful quantity, nothing but heat, minerals, and darkness. It took a while for the full picture to become clear, but eventually it did, and it remains one of the most beautiful ideas in all of biology. Certain bacteria had evolved a way to build energy not from light, but from chemistry itself, from the hydrogen sulfide pouring out of those vents. A process called chemosynthesis, distinct from the photosynthesis every plant on land depends on, using chemical energy instead of solar energy to build the basic sugars that life requires. Those bacteria became the foundation of an entirely separate food web, one with no connection to the sun at all. Larger creatures evolved to host those bacteria directly inside their own bodies, in a partnership so close it borders on becoming a single organism. And that partnership produced some of the strangest, most wondrous creatures ever found on this planet. Tube worms, for instance. Giant tube worms, clustered thickly around certain vent systems, can grow to nearly 3 meters in length. 3 meters, waving slowly in the mineral-rich water pouring from the vent nearby. And yet, remarkably, they have no mouth, no digestive system at all, in the traditional sense. Instead, their bodies are built almost entirely around a specialized organ packed with billions of the same sulfur-oxidizing bacteria found near the vent. Bacteria the worm feeds by absorbing hydrogen sulfide directly from the water through a feathery red plume at its tip, delivering it inward to its bacterial partners, who in turn produce the nutrients the worm needs to survive. It's a strange, quiet trade. The worm provides shelter and raw material. The bacteria provide food. Neither could survive that way alone. Together, in that scalding, mineral-rich water, they've built one of the strangest and most successful partnerships in the story of life on Earth. And the water itself, near these vents, can reach temperatures around 400 degrees Celsius. 400 degrees, and yet it doesn't boil. That sounds impossible until you remember what we talked about earlier tonight. Pressure. At those depths, the water pressure is so extreme that it raises the boiling point of water far beyond what it would be at the surface. So this scalding, mineral-saturated water pours out of the vent not as steam, but as a dense, dark liquid plume, sometimes appearing almost like billowing black smoke against the surrounding darkness, cooling rapidly as it mixes with the frigid surrounding seawater. And it's exactly at that boundary, that razor-thin transition zone between unbearable heat and near-freezing cold, that life clusters most densely of all. Feel your own skin for a moment, the temperature of the air around you right now, whatever it happens to be. It's almost certainly somewhere between 15 and 25 degrees. Comfortable, survivable, entirely unremarkable. Now imagine standing at the edge of water hot enough to melt certain metals, inches away from water cold enough to numb flesh in minutes, and imagine that razor's edge between those two extremes being, for entire communities of creatures, simply home. There are other strange residents around these vents too. Yeti crabs, pale, hairy-looking creatures, first properly described only in the early 2000s, that wave their claws slowly, rhythmically, almost like a strange underwater dance, back and forth through the mineral-rich water. For a long time, nobody quite understood why. Eventually, researchers realized the crabs were cultivating bacteria directly on the hairy bristles covering their claws, farming their own food source in place, then periodically scraping and eating the bacterial growth they'd cultivated. A crab, quietly gardening in total darkness, growing its dinner directly on its own body. And not far from many vent systems, in slightly different conditions, you'll find cold seeps instead, places where methane and hydrogen sulfide seep up gently through the seafloor without the extreme heat of a true hydrothermal vent, supporting their own separate chemosynthetic communities, mussels and clams and tube worms of slightly different species, all running on that same basic principle. Chemistry instead of light, patience instead of urgency, life, finding a way, using whatever raw materials happen to be available, wherever they happen to be found. Let's drift gently to one more source of deep-sea life before we continue our slow descent, because it's one of the strangest and most beautiful of all, and it begins, of all things, with a death. When a whale dies out in the open ocean, far from shore, its enormous body eventually sinks, down, down, through the twilight, through the midnight zone, settling finally somewhere on the abyssal plain, kilometers below the surface. And what happens next is called a whale fall, and it can sustain an entire, complex ecosystem for decades. At first, in the earliest months, larger scavengers arrive: sleeper sharks, hagfish, various deep-sea creatures drawn from kilometers around by the sudden, overwhelming abundance of food, a feast unlike anything most of them will ever encounter again in their lives, stripping the whale's soft tissue over the course of months, sometimes over a year or more. Then, once the soft tissue is gone, a second stage begins. Smaller scavengers, worms, crustaceans, tiny mollusks, moving in to consume what remains, colonizing the bones themselves, feeding on the last scraps of tissue clinging to the skeleton. And then, remarkably, a third stage begins, one that can last for decades. Specialized bacteria break down the fats and oils still locked deep inside the whale's bones, releasing hydrogen sulfide as a byproduct, the same chemical fueling life around hydrothermal vents. And that hydrogen sulfide, in turn, supports its own small chemosynthetic ecosystem: mussels, clams, tube worms, tiny creatures adapted specifically to feed on bacteria living off the slow, decades-long decomposition of a single whale's skeleton. A single whale fall, over its full lifespan, can support hundreds of different species. An entire small ecosystem, built from one death, sustaining life in that spot for longer than most human careers last, before finally, eventually, the bones are consumed entirely and the seafloor returns to its usual quiet emptiness, waiting for whatever might fall there next. There's something in that worth sitting with gently, without rushing past it. Even down here, in the coldest, darkest, most seemingly barren corners of this planet, an ending can become a beginning. A single death, falling slowly through kilometers of dark water, becomes decades of new life for hundreds of other creatures who never knew the whale at all, who simply arrived, patiently, to receive what it had to give. Feel the room around you one more time, the warmth, the particular ordinary safety of exactly where you are tonight. And then let's keep drifting downward, gently, towards zones deeper still, where the light disappears entirely, where the pressure grows heavier still, and where some of the strangest stories of this whole ocean are still waiting quietly in the dark, patient, the way they've always been, for as long as we care to listen for them. And down here, in this vast, dark middle stretch of ocean, something happens every single night that might be the largest movement of life anywhere on this planet, and almost nobody above the surface ever thinks about it at all. It's called vertical migration, and once you understand what it actually is, it becomes hard to look at the ocean the same way again, even from a beach, even just glancing at it from a boat. Every evening, as the sun sets somewhere above, billions upon billions of small creatures living in that twilight zone, tiny fish, shrimp-like crustaceans, jellyfish, countless other small drifting animals, begin rising upward, toward the surface, under cover of the fading light. They feed there, in the relative safety of darkness, among the richer waters near the top, where the actual living plankton grows. And then, as dawn approaches, they turn around and sink back down again, retreating into the safer, darker depths before the sunlight returns and exposes them to the predators that hunt by sight in daylight. This happens every single night, has happened every single night for longer than there have been humans to notice it. And in terms of sheer biomass moved, the sheer number of individual creatures involved, it is considered the largest daily migration of animal life anywhere on Earth. Larger than the wildebeest crossing the Serengeti, larger than any bird migration, larger by an enormous margin than anything visible happening on land at all, and it happens in near total anonymity, in darkness, beneath waves that never once betray what's rising and falling underneath them. Feel that for a moment against the quiet of your own room right now. Somewhere out there, right now, as you lie here, that migration might already be underway, or about to begin, depending on where in the world the sun happens to be setting at this exact hour. An event larger than almost anything that happens on land, occurring silently, invisibly, every single night, forever, without applause, without witnesses, simply because it works, and has always worked, and will keep working long after tonight ends. And it isn't just about feeding. This migration turns out to matter enormously for the entire planet's climate, in a way that took scientists a surprisingly long time to fully appreciate. Because when those countless small creatures rise to feed near the surface and then sink back down again by morning, they're not just moving themselves, they're moving carbon. Carbon they've eaten near the surface, carbon absorbed into their own small bodies, gets carried downward with them each morning, and a portion of it, through waste, through the creatures that die at depth, through countless small transfers along the way, ends up locked into deeper water, sometimes for centuries, sometimes far longer, removed from the surface, removed from the atmosphere, tucked away in the dark. This process, sometimes called the biological pump, moves an almost unbelievable quantity of carbon every single year, gigatons of it, shuttled downward by the quiet, repetitive, nightly commute of countless small creatures who have no idea, of course, that they're doing anything more than simply trying to eat without being eaten. And yet in doing exactly that, they're helping regulate the very climate of this planet, a service performed constantly, invisibly, by animals too small to individually matter, in numbers too large to properly imagine. It's strange, in a good way, to realize that something so vast and so consequential could be built from something so simple: small hunger, small fear of predators, multiplied by more individual lives than there are grains of sand on every beach combined, repeated every single night, forever. Let's rest here a moment and return to your body, to the room around you. Notice your own chest rising and falling as you breathe. That air you're breathing, some meaningful portion of the oxygen in it, came originally from the ocean, not from trees, as most people assume by instinct. More than half of Earth's oxygen is produced in the ocean, mostly by unimaginably tiny phytoplankton drifting near the surface, converting sunlight into oxygen exactly the way a forest does, just smaller, quieter, and far less visible. And yet, strangely, that same ocean, so full of oxygen near its sunlit surface, becomes almost entirely depleted of it as you descend. Somewhere between 200 and 1,000 meters down, in a band called the oxygen minimum zone, oxygen levels drop dramatically, low enough that most large active predators simply cannot survive there for long. It's one of the reasons creatures like the vampire squid, which we met earlier, can drift so peacefully through that particular layer. Almost nothing else wants to follow it there. Which means, in one of the ocean's stranger contradictions, some of the most oxygen-starved water on the entire planet sits directly beneath some of the most oxygen-rich water on the entire planet, separated by only a few hundred meters, a transition so complete it might as well be a different world. Let's talk about sound for a moment, because down here, where light fails almost entirely, sound becomes something else. something more important than it ever is to us, up in our sunlit, visually dominated lives. Sound travels faster in water than in air, significantly faster, roughly 4.5 times the speed. And there's a particular layer within the ocean, usually somewhere around 1,000 meters down, called the SOFAR channel, sound fixing and ranging channel, where temperature and pressure combine in just the right way to trap sound waves, letting them travel enormous distances with remarkably little loss of energy. Whales use this. Certain species can produce calls that travel not just kilometers, but potentially thousands of kilometers through that channel, whale to whale, across entire ocean basins, carrying messages we still don't fully understand, over distances that would be almost inconceivable for any sound produced in open air. Blue whales, the largest animals ever known to have existed on this planet, larger than any dinosaur, can produce sounds louder than a jet engine at close range. Low, deep, rumbling calls, pitched below the range of human hearing in many cases, that travel through that same deep sound channel across staggering distances, part of a conversation happening constantly, quietly, all around the globe's oceans, in a language built entirely from pressure waves moving through water that we are only just beginning to try to understand. Imagine, for a moment, being able to speak to someone on the other side of an ocean simply by making a sound, not through any device, just your own voice, shaped correctly, using the physics of the medium you live in as your amplifier. It sounds almost like magic. It's simply water, doing what water does, carrying vibration further and more faithfully than air ever could. Let's descend further now, toward the very bottom, because there's a fish down there that holds a record almost nobody expects. The deepest fish ever recorded, confirmed by video footage taken during a research expedition, was a snailfish, found living at a depth of over 8,300 meters, deeper than almost anything else with a spine has ever been documented. Small, pale, almost translucent, drifting gently along the seafloor in conditions that would seem, by every intuition we have, completely incompatible with vertebrate life. And it survives there through a strange adaptation. Snailfish living at extreme depth actually have skulls that are not fully solid, not fully closed the way ours are, but partially open, filled instead with a gelatinous, fluid-like substance. It sounds almost unsettling described that way, a fish with a liquid-filled head, but the reason is purely, elegantly practical. A rigid, air-containing skull, the kind most fish and all mammals possess, would be crushed at that depth, compressed by pressure 1,000 times greater than at the surface. A skull built instead around fluid, incompressible, pressure-neutral fluid, simply doesn't have that problem. There's no air pocket for the pressure to crush, because there was never an air pocket there to begin with. It's such a simple solution once you understand it. Don't fight the pressure. Don't try to resist it with strength, because nothing could resist 1,000 atmospheres and win. Instead, become something the pressure has nothing to push against. Fill every space with fluid, and let the pressure pass straight through you, harmlessly, the way it passes through the surrounding water itself. Many deep-sea creatures, in fact, avoid one very specific structure that most fish above them rely on entirely. A swim bladder, that air-filled internal organ that most fish use to control their buoyancy, floating effortlessly at whatever depth they choose. Down here, in the deep dark, an air-filled swim bladder would be a liability rather than a help, vulnerable to catastrophic compression under such extreme pressure. So many deep-sea fish have simply lost it altogether over evolutionary time, relying instead on fats and oils stored in their tissue, less efficient perhaps, but pressure neutral, safe, unaffected by depth, in the way a pocket of trapped gas never could be. There's a kind of wisdom in that, if you let yourself see it that way. Sometimes the strongest response to an overwhelming force isn't to resist it directly, it's to become something that force simply has nothing to grip onto at all. Let's surface, gently, for just a moment, back into the room around you, before we go further still. Feel your own skull, solid, protective, built the way it has to be built for a life lived at 1 atmosphere of pressure, under open sky, breathing air freely rather than water. It's easy to forget how specifically your entire body is built for exactly the conditions you live in, until you spend a little time considering a creature built, just as carefully, just as elegantly, for conditions that would instantly destroy you. Now let's talk about something else entirely. Something we didn't put there, but that has ended up down there all the same. The RMS Titanic rests at a depth of roughly 3,800 meters, in the cold, dark waters of the North Atlantic, discovered finally in 1985 after decades of failed searches. And in the years since its discovery, we've learned something strange and quietly poetic about what's actually happening to it, right now, tonight, as it has been happening for decades already. The ship is being consumed, not violently, not suddenly, slowly, patiently, by rust, and by something even stranger than ordinary rust. A particular species of bacteria, discovered specifically because of the Titanic itself, feeds directly on the iron in the wreck's hull, forming strange, delicate structures called rusticles, hanging like dripping icicles made of rust. Colonies of bacteria slowly digesting the great ship's steel skeleton, turning it, molecule by molecule, back into something closer to sediment than structure. Estimates suggest the ship could be substantially consumed, structurally, within a few more decades. The bow, the most iconic and recognizable part of the wreck, is already showing serious deterioration, sections collapsing slowly under the ship's own weight, as the metal holding it together grows weaker year by year. Eventually, within a human lifetime or so from now, the Titanic, as a recognizable structure, may simply cease to exist, dissolved gradually, patiently, by the same ocean that sank it in the first place, and by bacteria we didn't even know existed until we went looking at what remained of the ship they'd already begun consuming. And the Titanic, staggering as its story is only one wreck among what are likely thousands, scattered across ocean floors worldwide, most of them never found at all. Ships lost over centuries of trade, exploration, war, and simple accident, sitting quietly in the dark, some holding cargo untouched for hundreds of years, some holding stories nobody alive remembers anymore, waiting, the way everything down there waits, without any awareness of waiting at all. There's something almost sacred in that thought. The ocean floor isn't just geology and biology, it's also memory, layer upon layer of human history, preserved in cold and darkness far more effectively than almost anything left exposed on land, where wind and rain and time erode things quickly. Down there, in that stillness, things can last. Ships, cargo, occasionally, remarkably, entire settlements. Because in certain shallow coastal areas, submerged not by depth but by rising seas or shifting coastlines over thousands of years, archaeologists have found the remains of ancient human civilizations, streets, foundations, sometimes entire town layouts, preserved underwater, submerged slowly rather than destroyed suddenly, offering glimpses into human life from thousands of years ago that might never have survived at all if left exposed to open air. The ocean, it turns out, isn't only a place that takes, it's also, strangely, gently, a place that keeps. Let's rest in the room again for a moment. Notice, if you can, Some object near you tonight, however small, that has some age to it. Something older than you maybe, a piece of furniture, a worn book. Feel how differently time treats things that are simply left alone in open air, compared to things settled quietly into cold, dark water, forgotten, and in being forgotten, somehow preserved. And speaking of things preserved in strange, unlikely conditions, there's a feature of the deep ocean floor that behaves so strangely it seems to break the rules of what water is even supposed to do. In certain deep basins, particularly in the Gulf of Mexico, there are pools of water sitting directly on the ocean floor that are so extraordinarily salty, several times saltier than the surrounding seawater, that they behave almost like a separate liquid entirely. Because salt water is denser than regular seawater, these hypersaline pools don't mix with the ocean around them. They simply sit there, in distinct pools, complete with their own visible shorelines, their own gentle waves lapping against underwater banks, exactly like a lake sitting on the bottom of the ocean, submerged beneath kilometers of regular seawater above it. They're called brine pools, and they are, in the most literal sense, deadly to almost anything that swims into them. The water is so dense with salt, so depleted of oxygen, so saturated with toxic compounds like hydrogen sulfide and methane, that fish and other creatures that accidentally swim into a brine pool can die almost instantly, their bodies sometimes remaining remarkably preserved along the pool's underwater shoreline, unable to decompose normally in water that's hostile to bacterial life. And yet, right at the very edge of these deadly pools, along that strange underwater shoreline, life still gathers. Mussels, certain specialized worms, creatures adapted specifically to live right at that boundary, drawing chemical energy from the edge of the pool without ever fully entering it. The same basic chemosynthetic trick we learned about near the hydrothermal vents, applied here in an entirely different setting. Imagine standing at the edge of a lake that exists at the bottom of the ocean, its surface glinting faintly under whatever light your equipment provides, its shoreline lined with the pale, patient bodies of animals that have learned to live right at the boundary between something that sustains life and something that instantly ends it. It's a strange, beautiful, unsettling image, and it's real. It's down there right now, and there's still more waiting in that darkness. Methane, frozen solid under the crushing pressure and cold of the deep sea floor, forming something called methane hydrate, ice that remarkably burns when lit, a phenomenon researchers sometimes demonstrate by literally holding a flame to a chunk of what looks exactly like ordinary ice, watching it catch fire and burn steadily. Fuel trapped inside a lattice of frozen water molecules, existing in enormous quantities across certain regions of ocean floor, an energy source both fascinating and, to many scientists, a little worrying, given how much methane, a powerful greenhouse gas, remains locked away down there, stable for now, patient, the way everything down there is patient, but not necessarily permanent. Let's rest here for a breath before we go further, because we've been moving through a lot of strange, heavy corners of this world, and it's good, every so often, to simply come back up to the surface of your own attention for a moment. Feel the room again. Whatever light exists near you right now, however dim, the particular texture of whatever you're resting on, your own breathing, slow, steady, unhurried, that's still here. That hasn't gone anywhere, even while we've been drifting through trenches and shipwrecks and pools of water that kill on contact. You're still exactly where you started, safe, warm, ordinary, and that ordinariness is, itself, something worth appreciating quietly for a second, because there's something we haven't talked about yet that changes the whole shape of everything we've discussed so far tonight, and it has to do with just how little of this we've actually seen with our own eyes. Less than 0.1% of the deep ocean floor has been directly observed and studied in any real detail. Not mapped roughly through sonar, which we talked about earlier, but actually visited, examined, photographed up close by a camera, a submersible, a human being, or a machine sent specifically to look. 0.1%, which means, practically speaking, almost the entire deep-sea floor of this planet remains, at this very moment, completely unseen by anyone. And in the small sliver we have managed to examine, we keep finding things nobody expected. Every single year, scientists describe more than 2,000 new species discovered in the deep sea. 2,000 every year. And that number has held steady, or grown, for years now, without any sign of slowing down. Not 2,000 total. 2,000 new ones, discovered fresh, described formally for the first time, every single year, somewhere in that vast dark world we've barely begun to look at. And even that number, staggering as it is likely a small fraction of what's actually down there. Some estimates suggest there could be millions of species living in the deep ocean that we haven't discovered yet. Millions, not thousands. Millions of separate, distinct forms of life, each one with its own strange solution to living in darkness and pressure and cold. Each one entirely unknown to us, right now, tonight, going about whatever quiet business it goes about, completely unaware that it hasn't been named yet, completely unaware that it exists, in a sense, only partially, until the day someone happens to find it. It's strange to think about existing that way, fully real, fully alive, and yet somehow, from our perspective, not quite real yet, simply because no one has looked, as if reality itself were sitting there, patiently, waiting to be noticed, the way a room stays exactly as it is, whether or not anyone walks in to see it. This is part of why people sometimes call the deep ocean Earth's last true frontier, and it's not an exaggeration, not really. We've mapped Mars in more detail than we've mapped our own seafloor. We understand the surface conditions of Venus better than we understand what's living inside certain deep trenches scattered across our own planet. Space exploration captures the imagination, and rightly so. It's an extraordinary undertaking, but there is an entire alien-feeling world sitting directly beneath the ships we sail every day, mostly untouched, mostly unseen, right here, at home. Let's go a little deeper into why it's so hard to see, because the difficulty itself tells its own story. Most volcanic activity on this entire planet doesn't happen where we'd think to look for it, on land, in the famous volcanoes we've all seen photographs of. It happens underwater, along that same vast mountain range we talked about earlier tonight, the mid-ocean ridge, stretching more than 65,000 kilometers around the globe. Most of Earth's volcanic activity, most of its actual geological restlessness, happens in the dark, underwater, largely unseen, along cracks and ridges most people will never know exist. There are thousands of submarine volcanoes scattered across the ocean floor, some active, some dormant, some entirely unknown, until a passing survey happens to notice unusual seafloor topography or unexpected chemical readings in the surrounding water. Entire volcanic systems, entire geological events, occurring regularly, that simply never make the news, never get photographed, never become part of the story we tell ourselves about our own planet's activity, because they happen somewhere we mostly can't watch. One particular hydrothermal field, called the Lost City, discovered relatively recently in the middle of the Atlantic, works a little differently than the classic vents we described earlier. Rather than the intense volcanic heat driving those black smoke events, Lost City's chimneys form through a slower chemical reaction between seawater and the mantle rock beneath it, producing hydrogen and methane, instead of the sulfide-rich fluid of typical vents, at somewhat lower, though still substantial temperatures. And around those chimneys, an entirely different chemosynthetic community thrives. Different bacteria, different chemistry, different creatures adapted to this particular chemical recipe, proving that life down there doesn't just have one strategy for surviving without sunlight, it has several, multiple separate solutions to the same basic problem, discovered independently in different corners of the same dark ocean. And this idea that life can bloom entirely from chemistry rather than light has quietly become one of the most important ideas in an entirely different field of science: astrobiology, the study of where else in the universe life might exist. Because for a long time, the search for life beyond Earth was built almost entirely around the search for sunlight, for a planet sitting in what's called the habitable zone, close enough to its star for liquid water, warmed by direct starlight the same way Earth's surface is warmed. But hydrothermal vents change that thinking completely. If life here on Earth can bloom in complete darkness, powered entirely by chemistry rising from inside the planet itself, then maybe sunlight isn't actually a requirement for life anywhere. Maybe it's just one option among several. And that idea has turned scientific attention towards some very unlikely candidates elsewhere in our own solar system. Europa, one of Jupiter's moons, believed to hold a vast liquid ocean beneath its frozen icy shell, an ocean that may never see a single photon of direct sunlight, sealed away under kilometers of ice, and yet an ocean that could, plausibly, host hydrothermal vents of its own, driven by tidal heating rather than solar warmth, potentially capable of supporting exactly the kind of chemosynthetic life we've found thriving here on Earth's own ocean floor. Enceladus, a small icy moon of Saturn, shows something even more directly suggestive: plumes of water vapor and ice, erupting from cracks near its south pole, spraying out into space, carrying with them chemical signatures that suggest an ocean beneath its icy crust, an ocean interacting with a rocky seafloor in ways that could produce the exact same hydrogen-rich chemistry that fuels vent ecosystems here at home. Which means, and this is worth sitting with for a moment, in the quiet of your own room tonight, that the search for alien life may not actually depend on finding another Earth, sunlit, warm, familiar. It might depend instead on understanding places exactly like the ones we've been drifting through tonight: cold, dark, sunless, places where the only light comes from the creatures themselves, and the only energy comes from the chemistry of the rock below rather than the star above. In a strange, quiet way, exploring our own deep ocean might be one of the closest things we have to visiting another world, without ever having to leave this one. Let's come back to the surface of your attention again, gently, for a moment. Feel your own body resting there, warm, breathing, alive in a world built on sunlight, the way most familiar life is built. And hold, alongside that, the idea that somewhere close by, in the same ocean whose waves you might have walked beside once, there are entire ecosystems built on a completely different foundation, proving that life, whenever given even the smallest opening, tends to find a way through. There's one more layer to visit tonight before we let this particular part rest, and it has to do with a creature that manages to bridge two entirely different worlds at once: the world of air and light we live in, and the world of pressure and darkness we've been exploring. Sperm whales are air-breathing mammals, exactly like us in that basic sense, needing to surface regularly to breathe. And yet they are also, remarkably, among the deepest diving animals on this entire planet, capable of descending to depths of around 3,000 meters, deep into that true midnight zone, holding their breath for as long as 90 minutes at a time, hunting giant squid and other deep-sea creatures in total darkness before returning, patiently, steadily, back up toward the surface for air. To survive dives that deep, sperm whales have evolved lungs that actually collapse, deliberately, safely, under the pressure, rather than resisting it and risking catastrophic injury. Their ribcage is flexible enough to allow this collapse without damage. Oxygen, instead of being stored primarily in the lungs the way it is for us, is stored largely in their blood and muscle tissue, in far higher concentrations than in most other mammals, allowing them to function for extended periods without needing to draw a single breath. And by allowing their lungs to collapse rather than resist the pressure, they avoid a problem that plagues human divers, even at far shallower depths: the risk of nitrogen dissolving dangerously into the bloodstream and forming bubbles on ascent, a condition we call decompression sickness, or the bends. Because their lungs collapse fully, forcing air out of the alveoli where gas exchange happens, before the nitrogen has a real chance to dissolve into their blood in dangerous quantities. Sperm whales largely sidestep the very danger that makes human deep diving so genuinely perilous without careful, slow, gradual ascent. There's something almost moving about that image, if you let yourself sit with it. A warm-blooded, air-breathing, deeply intelligent mammal, closer in some fundamental biological sense to us than to any fish, diving down into a world of crushing pressure and absolute darkness that would instantly destroy an unprotected human being, hunting there, patiently, in silence, for creatures most of us will never see even a photograph of, and then returning, calmly, back to the surface, back to air, back to light, before diving down again. It's a reminder that the boundary between our world and that dark one isn't always as absolute as it seems. Some creatures move between both, comfortably, adapted specifically to bridge that impossible-seeming gap. And on that thought, gently, let's pause here for a while. And that thought, about boundaries, about creatures that move between two impossible worlds, brings us to something else worth sitting with tonight. Something about the ocean's history, rather than just its geography. Because the ocean isn't only a place, it's also a kind of memory, layered the way sediment layers itself, patiently, over unthinkable stretches of time. If you could take a long, narrow column of sediment from the deep seafloor, drilled carefully, brought up intact, you'd be holding something closer to a book than a rock. Each layer, pressed thin, sometimes only millimeters, representing hundreds or thousands of years, holds traces of what the ocean and the atmosphere were like at that exact moment in Earth's long, slow story. Ash from volcanic eruptions, shells from tiny creatures that lived and died and drifted down as marine snow, chemical signatures locked into those shells, carrying whispers of ancient ocean temperature, ancient carbon dioxide levels, ancient conditions from a world so different from ours that it can be hard to picture at all. Scientists read these cores the way you might read growth rings in an old tree, except instead of counting a few hundred years, they're sometimes reading millions. Ice cores, drilled from deep within polar glaciers, work in a similar way, trapping tiny bubbles of ancient atmosphere, actual samples of air breathed by no one, sealed away and preserved for hundreds of thousands of years, waiting patiently until someone finally drilled down far enough to let them out again. Together, ocean sediment cores and polar ice cores have completely reshaped what we know about the planet's climate history, not through guesswork, through direct physical evidence, carried gently downward, layer by layer, year by year, in that same slow snowfall we talked about earlier tonight, and simply left there, undisturbed, until we finally learned how to ask it the right questions. There's something quietly moving in that. This ocean we've been drifting through tonight isn't just alive in the present tense. It's also an archive, a library with no reader for most of its existence, holding the story of this entire planet, waiting the way everything down there waits, without impatience, without urgency, simply persisting until the day someone finally arrives to listen. Let's return, gently, to scale for a moment, because it's easy to lose the size of all this in the middle of individual stories. The Pacific Ocean alone is larger than every single landmass on Earth combined. All the continents, all the islands, put together, and the Pacific still wins, still stretches wider, still holds more space within its boundaries than all dry land on the entire planet added together. It's a strange thing to actually feel, rather than simply know. We tend to picture our world as land, dotted here and there with oceans in between. The truth is closer to the reverse. Ocean, with small scattered patches of land rising just above its surface, patches we happen to live on, patches that feel, from where we stand, like the whole story, when really they're the smaller half of it. And the average depth of all this ocean, taken across its entire surface, isn't shallow at all. It comes out to somewhere around 3,688 meters. Not the deepest trench, the average. If you smoothed out every mountain range, every trench, every shelf, and ridge and plain, and asked, on average, how deep is the water covering most of this planet, the answer would be nearly 3.5 kilometers straight down. Here's a way to feel that more directly. If Earth's entire surface, land included, were somehow smoothed out perfectly flat, no mountains, no valleys, just a uniform sphere, the water currently sitting in the oceans would be enough to cover the entire planet completely, to a depth of about 3 kilometers. Every square meter of this whole world, submerged 3 kilometers deep, if only the land would agree to lie flat and let it happen. We live, in other words, on a water world that simply happens to have enough irregular high ground poking up above the surface for us to build our lives on. It's a small, stubborn exception, our dry land, rather than the rule. Let's rest in the room again for a second, because these numbers can start to feel abstract if we don't keep returning to something physical, something felt. Look, if you can, at whatever's closest to you right now. A wall, a window, some solid, dry, unmistakably land-based thing. That's the exception. That's the small, comfortable anomaly you happen to be sitting on top of tonight, floating, in a sense, on a thin shell of dry rock, poking up out of a planet that is otherwise almost entirely, overwhelmingly, water. And that water has been here for a very, very long time. Life itself, as far as we can tell from the oldest evidence we've found, first appeared in the ocean more than 3.5 billion years ago. 3.5 billion. A number so large it stops being countable in any meaningful sense and simply becomes a kind of texture, a feeling of depth rather than a specific quantity. For context, if you compress the entire history of Earth into a single 24-hour day, life would have appeared in the ocean sometime in the very early morning, and everything we consider human history, every war, every invention, every person who has ever lived, would occupy less than the final second before midnight. The ocean was here first. Life began there first. And in some very real sense, everything that followed, everything that eventually crawled onto land, grew lungs, grew legs, eventually stood upright, and looked back out at the water it came from. All of it is simply the ocean's own story, continuing to unfold, on dry ground, for a little while. There's a particular kind of quiet in that thought. Not sad, not frightening, just old. the way certain very old houses feel when you walk into them, not haunted exactly, just carrying a weight of time that makes your own life feel briefly, gently, smaller, and somehow that smallness doesn't feel bad at all. It feels almost like being held. Let's talk, gently, about something more recent in that long story. Something happening right now, this decade, that concerns that vast, dark floor we've been exploring tonight. Scattered across certain regions of the deep, abyssal plain, potato-sized lumps called polymetallic nodules lie scattered across the sediment, sometimes in astonishing density, carpeting the seafloor for enormous distances. These nodules form incredibly slowly, growing perhaps a few millimeters every million years, as minerals dissolved in the surrounding water slowly precipitate out, layer by layer, around some small fragment at their core, a shark's tooth sometimes, or a tiny piece of rock, patiently accumulating metal, atom by atom, across geological stretches of time, almost too long to properly imagine. And inside those slow-growing nodules sit valuable metals: manganese, nickel, cobalt, copper, metals increasingly important for modern technology, for batteries, for electric vehicles, for the machinery of a world trying to move away from fossil fuels, which has led, in recent years, to growing interest in deep-sea mining, harvesting these nodules directly from the ocean floor at industrial scale. And that interest has created real, serious concern among many of the scientists who study these ecosystems, because we still understand so little about what lives down there, about how disturbing that ancient, slow, patient seafloor might ripple outward into ecosystems we haven't even finished discovering yet. Nodules that took millions of years to form could be stripped away in a matter of years, along with whatever specialized, still unnamed creatures depend on them, in ways we might not fully understand until long after the damage has already been done. It's not a simple story, and it doesn't resolve easily into something to feel calm about. It sits, instead, as an open question, one still being debated by scientists, by policymakers, by entire nations with competing interests, about how to weigh what we need against what we don't yet understand we might be losing. Sometimes the honest thing to say, in the quiet dark, is simply that we don't know yet, and that not knowing yet deserves caution rather than haste. Let's soften, gently, and come back towards something a little more still, because for all the human activity now reaching down into these depths, mining interests, shipping traffic, deep-sea cables carrying nearly all of the world's internet data along the ocean floor in thin, quiet lines, the deep ocean, for most of its history, and for most of its vast, unexplored expanse even today, remains one of the quietest, most naturally undisturbed places on this entire planet. There's a low, constant, barely perceptible rumble that moves through deep ocean water, background noise from distant seismic activity, from waves breaking somewhere impossibly far above, from the slow churn of currents moving heat and salt around the globe. It's not silence exactly. Nothing in nature is ever quite that, but it's close. A stillness so complete that it becomes its own kind of presence, the way a very quiet room at night can feel less empty than full of something you can't quite name, just stillness itself, existing as a thing. That natural quiet, though, has been changing. Human-made noise, from shipping traffic, from sonar, from industrial activity, has measurably altered the deep ocean's soundscape over the past century, adding a layer of noise pollution to a world that evolved, for hundreds of millions of years, in near total quiet. For creatures like whales, who depend so heavily on sound, on that vast oceanic conversation carried through the SOFAR channel we talked about earlier, that added noise isn't a small thing. It can drown out calls meant to travel thousands of kilometers, disrupt communication, disrupt migration, disrupt behaviors so ancient and so essential that we're still only beginning to understand what we might be interrupting. It's worth sitting with that gently, without turning it into something heavier than it needs to be tonight. Just noticing it, just letting it sit there quietly, the way most difficult truths deserve to sit, without demanding to be solved this instant, in this room, at this hour. Let's return, one more time tonight, to the physical space around you. Feel the quiet of your own room, if it's quiet. Feel your own breath, slow, easy, untroubled. There is a kind of stillness available to you right now that echoes, faintly, the stillness of that deep water far away. And there's nothing wrong with letting yourself borrow a little of that. Letting your own evening grow quieter and quieter, the way that ocean does, layer by layer, the further down you allow your attention to drift. And there is still more to explore tonight, more creatures, more strange, patient adaptations, more of that vast unmapped floor, waiting the way it always waits, without needing anything from you at all, except, perhaps, a little more of your attention, a little longer. Let's go deeper still, past even the abyssal plain, down into the true trenches, into the hadal zone itself, because there's something happening down there, in the very deepest cracks of this planet, that quietly rewrites what we think life is even capable of enduring. Remember the name, Hadal, named for Hades, the underworld, and it's hard not to feel that the name was chosen with real feeling, real recognition, rather than as some dry scientific label. Because at those depths past 6,000 meters, existing only within the narrow, isolated confines of ocean trenches scattered here and there across the globe, the pressure becomes so extreme that it stops being simply a difficult condition to survive and starts becoming an active force, actively reshaping biology at the cellular level. At those pressures, ordinary cell membranes, the thin, flexible boundary holding every living cell together, begin to behave strangely. Normal membranes are built from fats, arranged in a particular flexible structure, fluid enough to let nutrients pass through, proteins embedded and moving freely within them. But extreme pressure squeezes those membranes, packs the molecules more tightly together, stiffens them in ways that can, in ordinary organisms, disrupt basic cellular function entirely. Enzymes stop folding correctly. Proteins stop working the way they're supposed to. Life, at a fundamental molecular level, starts to come undone. And yet creatures live down there. Not just survive, briefly, in some marginal, barely clinging on sense. Live, function, reproduce, persist, generation after generation, at depths where a human body would be crushed instantly and completely, not gradually, not painfully, simply and immediately, the way a paper cup collapses under a boot. The secret, it turns out, lies in a particular molecule many hadal organisms have evolved to accumulate in astonishing concentrations. A compound called TMAO, trimethylamine oxide, which acts almost like a molecular counterweight, stabilizing proteins and membranes against the crushing effect of extreme pressure, essentially propping cellular structures back open against a force that would otherwise squeeze them shut. The deeper an organism lives, generally, the more TMAO its tissues contain, almost as if each species carries a kind of internal pressure gauge, calibrated with striking precision to the exact depth it calls home. There's something almost moving in that precision, not a general toughness applied broadly and imprecisely, a specific, elegant molecular solution, fine-tuned species by species, depth by depth, matching exactly the pressure each creature actually needs to withstand, no more, no less. Evolution, working patiently, over unthinkable stretches of time, solving the exact same brutal physical problem again and again, slightly differently, for every different depth, every different trench, every different creature that ever attempted to live there. And it isn't only pressure these creatures have had to solve for. In certain colder regions of the deep ocean, particularly toward the poles, some fish have evolved something even stranger: natural antifreeze, produced directly within their own blood. These fish carry specialized proteins that bind directly to tiny forming ice crystals within their bloodstream, preventing those crystals from growing larger, effectively stopping their own blood from freezing solid, even in water that sits at temperatures that would freeze ordinary blood almost instantly. It isn't a metaphor, it's a literal biological antifreeze, evolved independently in several different unrelated groups of fish, facing the exact same brutal cold. In exactly the same practical way, nature so often arrives at similar answers to similar problems, again and again, wherever the same pressure is applied. Feel your own blood for a moment. Warm, 37 degrees, utterly unremarkable to you, because it's simply always been that way, your entire life, without exception. Now imagine blood that has had to learn, slowly, across countless generations, how to actively resist freezing solid inside a body, swimming through water, cold enough to end nearly any other form of life within minutes. That's not a small adaptation. That's an entire branch of biology, quietly rewriting the basic rules of what blood is even supposed to do. Let's drift back to the Hadal trenches once more, because there's one particular question that scientists have wondered about for a long time, and it connects, gently, all the way back to where this whole story began. If life can exist at pressures 1,000 times greater than what we experience, in water near freezing, in complete and total darkness, feeding on nothing but scraps drifting down from far above, how did life begin in the first place? Not just where it lives now, but where it might have first appeared, billions of years ago, on an early Earth that looked almost nothing like the world we know today. And increasingly, many scientists believe the answer circles back to those same hydrothermal vents we spent time with earlier tonight. Because those vents don't just support life today, they may have provided exactly the right conditions for life to first assemble itself. All that unthinkable time ago. Think about what a vent actually offers: a steady source of chemical energy, independent of sunlight, which didn't reliably penetrate early Earth's atmosphere the way it does today. Warm, mineral-rich water flowing continuously through porous rock formations, creating countless tiny chambers, almost like natural laboratories, where chemicals could concentrate, react, and interact repeatedly over long stretches of time. And crucially, a steep, stable gradient, a difference in chemistry and temperature between the vent fluid and the surrounding seawater, the exact kind of gradient that living cells still use today to generate energy, in every single cell of your body, right now, as you lie here breathing. In laboratory experiments designed to recreate these vent-like conditions, researchers have found that RNA molecules, the same basic molecular building blocks life still relies on today, can form and even show early signs of self-organizing behavior under conditions closely mimicking those found near hydrothermal vents. It's far from a complete answer, far from a settled question. Science rarely offers a moment that clean, that certain, but it suggests, gently, persuasively, that the same strange dark world we've been drifting through tonight, full of tube worms and yeti crabs, and water hot enough to melt certain metals without ever boiling, might also be, in some very real sense, the birthplace of everything. Which means, if you let that idea settle all the way down, that everything alive today, every plant, every animal, every person who has ever lived, including you, right now, lying there in whatever room you happen to be in, might trace back, ultimately, to some small, patient chemical reaction occurring in the dark, near a crack in the ocean floor, billions of years before there was any word for dark, or ocean, or floor, or before there was anyone at all to notice, or wonder, or ask. There's a particular kind of stillness that comes with a thought like that. Not smallness exactly, something closer to belonging, as if the deep, dark, crushing, cold, largely unexplored ocean we've spent this whole evening drifting through isn't separate from you at all. It's where you, in some very distant, very literal sense, actually began. Let's come back to the room now, slowly, gently, the way we keep returning, again and again tonight, because that return matters just as much as the descent itself. Feel your own body again, warm, breathing, whole. You are, in this exact moment, the product of 3.5 billion years of patient, unbroken continuity, stretching all the way back to some small chemical spark near a vent in a young, dark ocean, and every single link in that unbroken chain, every single ancestor, however small, however strange, however unrecognizable to you now, managed, somehow, to survive long enough to pass life forward, one more generation, until eventually, improbably, it reached you. That's not nothing. That's not a small thing to carry into sleep tonight. And there is still more waiting for us. More of that vast, unmapped floor. More creatures adapted to conditions we've barely begun to understand. And slowly, gradually, the beginning of our long, patient journey back upward, back toward the light, back toward the surface, back, eventually, toward this very room. Let's stay a moment longer at this depth, though, because there's one more strange feature of the seafloor worth visiting before we start our long climb back upward, and it involves something that seems, on the surface of it, almost impossible. Fresh water, rising up out of the salt ocean floor itself. In certain locations, mostly along coastlines where porous limestone extends out beneath the seabed, freshwater springs bubble up directly through the ocean floor, sometimes with enough force and volume that sailors in ancient times knew about them, occasionally even used them, lowering barrels down to collect drinkable water from what looked, from above, like completely ordinary open sea. The water comes from rain falling on land, sometimes kilometers away, soaking down through underground rock formations, traveling slowly through hidden channels, and finally emerging, quietly, unexpectedly, from cracks in the seafloor, far from any visible shore. There's something gentle in that image, worth holding for a second. Even in the middle of all that salt, all that pressure, all that vast, undifferentiated ocean, there are still these small, persistent threads of fresh water, arriving from somewhere else entirely, rising up through the dark, carrying a little piece of rain that fell perhaps months earlier, over hills the ocean will never touch directly. Water finding water. A kind of quiet reunion happening constantly, in places almost nobody ever thinks to look. And that idea of connection, water everywhere linked to water everywhere else, however far apart it might seem, brings us to something worth remembering about the ocean's role in this planet's temperature, something almost too large and too constant to properly notice, the way you don't notice your own heartbeat until someone asks you to. The ocean absorbs an enormous amount of the sun's heat every single day, more than the atmosphere itself, storing it, moving it slowly around the globe through vast, patient currents, releasing it gradually, unevenly, over months and years, rather than all at once. It's the reason coastal regions tend to have milder weather than places deep inland, the ocean acting as a kind of enormous thermal reservoir, absorbing extremes, softening them, releasing warmth slowly back into the air during winter, absorbing excess heat slowly during summer. Without that vast, patient, quietly regulating body of water surrounding and threading through this planet, the swings between hot and cold, between day and night, between season and season, would be far more violent than anything we currently experience. You've lived your entire life inside that regulation without ever really having to think about it. The mildness of an evening breeze near a coastline, the reason winters inland can turn brutal in a way winters near open water rarely do, all of it, quietly, patiently, managed by that same vast body of water we've been drifting through tonight, doing its slow, invisible work, regardless of whether anyone above ever stops to notice or say thank you. Let's feel the room again for a moment, gently, because this next stretch of tonight's story begins, at last, to turn upward. We've been descending, layer by layer, for a long while now. Sunlight zone, twilight zone, midnight zone, abyssal plain, hadal trench, down into pressures and darkness far beyond anything a human body could survive unprotected. And down there, at the very bottom, we found not emptiness, but a strange, patient fullness. Life persisting in conditions that seemed, on paper, to make life impossible. Chemistry standing in for sunlight, molecular counterweights standing in for strength, slowness, patience, scarcity, turned not into weakness, but into a whole different way of being alive. And now, slowly, we begin to rise. Not quickly. Nothing about the ocean moves quickly, not really. Not even the fastest currents. Not compared to the age of the water itself, some of which has been circulating through deep, cold currents for 1,000 years or more, before finally surfacing again, breathing air for the first time in a millennium. So let's rise the same way, slowly, gently, layer by layer, back the way we came, but seeing it now with everything we've learned along the way. Back up through the hadal zone, past trenches holding fish with fluid-filled skulls, and blood chemistry precisely tuned to the exact pressure of their particular crack in the earth. Back up past the abyssal plain, scattered with slow-growing nodules that took millions of years to form, and whale skeletons quietly nourishing communities that took decades to arrive and will take decades more to finish. Back up past the midnight zone, past creatures with eyes built entirely for scarcity, past anglerfish drifting alone with a single small light glowing patiently in the dark, waiting, the way everything down here waits, for something to happen. Back up into the twilight zone, where blue light still faintly persists, where billions of small creatures are perhaps, even now, at this exact hour, beginning their nightly rise toward the surface, carrying carbon downward again by morning, quietly regulating a planet's climate through nothing more than simple hunger and simple fear. And finally, back up into the sunlight zone, where color returns, where warmth returns, where the ocean starts to look, finally, like the ocean most of us picture when we hear the word. Familiar, bright, alive, in a way that doesn't need explaining, or context, or careful adjustment of expectation. There's something worth noticing in that ascent, something that mirrors, quietly, the shape of this evening itself. We started in your own room, warm and lit and safe, and traveled downward into darker and stranger and more difficult places, and now we're rising back up again, toward light, toward familiarity, toward the surface, the same way you, tonight, will eventually rise up out of whatever thoughts and worries followed you into this room, and settle, gently, back into rest. We're not there yet. There's still more to see on the way up, more still waiting quietly in these different zones we're passing back through, more of that vast, largely unmapped floor stretching out beneath us, even as we rise away from it, patient, ancient, unbothered by our leaving, exactly as unbothered as it was by our arrival. And this is where we finally arrive back in the sunlight zone completely, floating just beneath the surface, close enough now to feel the difference in the water itself. Warmer, brighter, moving with the gentle chop of waves rather than the stillness of the deep. Before we break the surface completely, let's gather a few last threads, because a few things deserve to be said plainly, without metaphor. The way you might say something simple and important to someone right before they fall asleep. The ocean holds roughly 97% of all the water on this entire planet. 97%, which means nearly everything you think of when you think of water, rivers, lakes, the rain that falls on your own roof sometimes. All of that together makes up only a small remainder, a few percent, borrowed temporarily from the vast ocean reservoir before eventually finding its way back. Nearly all the water that has ever existed on Earth is out there right now, in that same ocean we've spent all evening drifting through, and always has been, cycling slowly, patiently, through sky and cloud and river, and back to sea again, over and over, for billions of years. And that ocean, when you consider not just its surface area, but its actual three-dimensional volume, top to bottom, coast to trench, is the single largest habitat for life anywhere on this planet, larger than every forest combined, larger than every grassland, every desert, every mountain range. Most of the living space available to life on Earth isn't on land at all. It's held within that vast, dark, quiet volume of water, most of it entirely unlit, entirely unexplored, and yet, as we've spent this whole evening learning, entirely alive. It's strange and a little humbling to realize that for all of human history, all of human civilization, all the cities and roads and quiet bedrooms like the one you're resting in right now, we've built our entire understanding of the world around a thin, sunlit sliver of a much larger, much darker, much older place. Almost everything that has ever lived, in terms of sheer space available for living, has lived somewhere we've never even seen. And that darkness, vast as it is, has never once been empty. That's the thread running through absolutely everything we've explored tonight. Every zone, every pressure, every temperature, every impossible seeming condition met not with absence, but with some quiet, patient form of life, finding a way through. The ocean floor holds more of Earth's actual story, layered gently into its sediment, than any library ever built by human hands. Every book we've ever written together wouldn't equal the record quietly kept in a single meter of undisturbed seafloor, holding, in careful mineral layers, the true and complete memory of this planet's climate, stretching back further than any human language. We're almost at the surface now. Feel it, gently, the way you'd feel the very last moment before waking from a long, slow dream, except reversed, because we're heading toward rest now, not away from it. The water grows brighter above us, warmer, familiar, in the way sunlight always feels familiar, no matter how far you've traveled to get back to it. And when we finally break the surface, quietly, without splash, without announcement, we find ourselves exactly here, in your room, in this exact moment, this particular evening, with its particular soft light, or particular gentle dark, its particular blanket, its particular quiet. The deep ocean is still down there right now, patient, ancient, largely unknown, and likely to remain that way for a long while yet, no matter how many more expeditions we send, no matter how many more nodules or vents or trenches we eventually map. That vastness isn't a problem waiting to be solved. It never was. It's simply a gift, quietly offered, to anyone willing to imagine it, to sit with it, to let its scale soften something in their own chest for a few minutes before sleep. You don't need to remember all 100 of the things we visited tonight. You don't need to hold on to the numbers, the depths, the names of creatures you'll likely never see. What matters, if anything does, is simpler than that. Somewhere, right now, in complete darkness, at pressures that would fold you instantly, something ancient and patient is drifting slowly through cold water, entirely unaware of you, entirely unaware of anything really, just existing, the way you are about to simply exist for a while, without effort, without agenda, without needing to do anything at all except rest. The room around you is safe, the blanket is enough, the breath moving quietly in and out of your body is enough. Let the ocean stay where it is, deep and dark and unbothered, holding its mysteries a little longer, the way it always has, the way it always will. And let yourself, now, gently, do the same. Rest now.